So let's draw each of these curves that they're talking about. Y equals x, that's just this diagonal line. Y equals 2, that's this horizontal line. Then x equals 0, that's this vertical line. So the region contained between those three things is this region right here. Okay, so if we're asked to find the volume of that region, and then it's rotated around the x-axis, that means you're thinking about this two-dimensional triangle rotating, so changing into the third dimension by moving towards you, like out towards your, past your computer screen, and then rotating back away behind your computer screen, then making a full circle. Okay, so when we do these, we're revolving them. That means they're making that circular type motion. So we have a three-dimensional shape that can help us find that volume. So we can find the volume of an infinite amount of right cylinders, and I'll show you how that'll help us. So here's a right cylinder. This is traditionally how it was drawn, from at least in my education. This is your radius, right? And then this would be the height of the right cylinder. But it's the same formula if you tilt that right cylinder on its side, right? So this is your h, and then this would be your radius. Let me see, because right now, if we draw a right cylinder, it would get some area that we don't want. So here, I'm going to draw a right cylinder from here to here, and that right cylinder is going to capture the volume of that figure that's being rotated. But in its current form, this right cylinder, looks like this, is capturing some area that we don't want, like all this white space. So the way we're going to handle that in this question is that we're going to find the volume of this entire figure. Oops, there we go. So this gets rotated from x equals 0. Where do we end? At x equals 2, because if we plug in 2 in here to find out where they intersect, you get x equals 2. So we're going to find the volume of this entire right cylinder that's being revolved, the big one, okay, which includes some area that we don't want. And then if we find the volume of just this area being rotated around the x-axis, we can subtract that from the big right cylinder, and that will be the area that we wanted, this shaded area. Okay, so the big right cylinder that encompasses both this area and this area, it has a radius of 2, right? So here's the right cylinder I'm envisioning. Sorry about that extra there. Yeah, so from here to here, that has a radius of 2. And then the height is also 2. This distance right here is 2. Okay. So the volume, including both the shaded area that we want and this area that's not shaded that we don't want, is pi r squared h. So that's 8 pi. So what we want to do is take that entire area that's been revolved around the x-axis, and then since we can't easily get to this area with the right cylinder, we're going to find this area here that I'm making with these black hash marks and revolve that around the x-axis. And once we find that volume, we can subtract that from 8 pi, and that will leave us with the shaded area. Okay, so to find this area, each right cylinder we draw depends on that diagonal line. Right, so here's a right cylinder. So that's one right cylinder. That's what we want. This is another right cylinder that we would want. Okay, but since we can't just take like a right cylinder of length 0.5, another right cylinder of length of a height of 0.5, there'd be error there, right? Where we've got some gaps. We want to take an infinite amount of those right cylinders, and so what we're going to do is we're going to say these heights are infinitely small. That way we can use an integral to help us find out the total volume. So we're integrating with respect to the x-axis. We start at x equals 0 for our figure that we're trying to revolve, and it ends at x equals 2. And then we're taking an infinite amount of right cylinders. So here's the formula for a right cylinder. Pi, and then the radius is depending on this right here, right? Because the radius of this one is smaller than the radius of this one that I drew. Okay. So the radius is y equals x. So wherever we are on the x-axis, that tells us how high we are, because that if you plug in 2 in for x, you get out 2 in for y. If you plug in 1 in for x, you get out 1 in for y. The y values are the radius. So it's pi x squared times h. We said those heights are infinitely small. So that's the volume of the infinite amount of right cylinders from 0 to 2. Okay, so the rest of this is pretty easy compared to setting the whole thing up, right? This is pi x to the third over 3 for the antiderivative, and I evaluate that from 0 to 2. And then here I'm going to plug in 2, so 2 to the third is 8 pi. I need to subtract what happens when I plug in 0, but that's just going to be 0. So I've got 8 pi over 3 subtracted by, that's 8 pi subtracted by 8 pi over 3. So getting common denominators, that's 24 pi over 3 minus 8 pi over 3. So 24 minus 8 makes 16 pi over 3. And so that's the volume of this red shaded region revolved around the x-axis. Okay, and again, the reason is the reason for this extra little bit of information is that this is the entire region, both this black shaded region and the red shaded region revolved. And then we subtracted what I'm shading as just the black shaded region revolved around the x-axis. That left us with the red shaded region.